Once again, welcome to a new problem. This time we have a column, it's a marble column, and it happens to stand at 8.6 uh, meters. That's the height of the column. This is 8.6 meters. And also the cross-sectional area right here. Uh, the cross-sectional area of the column A is given as 1.4 meters squared, and the it supports, so there's a mass placed on top of it. So there's a mass placed on top of it, um, and that mass happens to be equivalent to 25,000 kilograms. And we can always change that right away into a force. So F equals to mg. Remember, g is the acceleration due to gravity. So we're going to take that 25,000 kilograms and then we multiply that by 9.8 meters per second squared, and 9.81 to be precise. And that gives us 245 250 newtons. That's the force being applied. The first thing, so this is the information we're given. The first thing we want to find out is the strain, or rather the stress, that's being provided on the column. And then the second thing, we want to find the strain. And eventually we want to find delta L, meaning if you're applying a force on the column, then it shrinks. And so we want to find out by how much it shrinks, and we're calling that delta L. Okay, we're calling that delta L. Just as a reminder, this is the initial length of 8.6 that we're using. And so by definition, stress is the force being applied on the marble, on the column itself. So stress is the force over the area itself. And we use sigma as a symbol for that. So the force is 245,250 newtons, and we divide that by, just want to make sure this is clear, this is 250 newtons. We divide that by 1.4 meters squared, and we end up having sigma, or stress. Remember, stress and sigma are the same, equivalent to 1.7 times 10 to the 5 Newton per meter squared. Next thing, so we've dealt with the stress, which is, if you think about a unit area of 1 meter squared, what's the force being applied within that unit area? So that's how we define the stress itself. The next part of the problem, we're going to do it on the second page, and here we're interested in finding the strain. But before that, we can define E, which is the Young's modulus of elasticity, and we're going to use that route to get the strain, because Young's modulus of elasticity relates the stress, which is sigma, to the strain, which is epsilon. Okay, so this is the strain itself, and given that relationship, you can see that epsilon simply becomes the strain of a Young's modulus. We already know what the strain is from the previous page. It happened to be 1.7 times 10 to the 5 Newton per meter squared. And then, of course, Young's modulus is is given for this marble. Young's modulus is given as 50, um, 50 times 10 to the 9, 50 times um, 10 to the 9 Newton per meter squared. When we divide those two numbers, we end up getting epsilon, which is this the strain being equivalent to 3.4 times 10 to the -6. And we don't have units for the strain because it's just a relationship between the stress and Young's modulus. In the next and final page, we're gonna go ahead and define strain in terms of change in length over the original length. So what we're saying is, if we have the column and it's being pushed by a force, it has an initial length. Eventually, what's going to happen is that uh, that force is going to shrink it to a new level. So it shrinks to a new level. And so more than anything, we're interested in this specific displacement right here. That displacement is what we're calling delta L. Okay, and we've defined strain in terms of delta L. We already have the value of the strain, so we can go ahead and solve for delta L by multiplying the strain by the original length, which you're thinking of it as Li, but it's not. So E, which is 3.4 times 10 to the -6 times 10 to the -6, and then you go ahead and multiply that by the original length. As you can recall, it was 8.6 meters, and that gives us a value for how much it's going to shrink, which is 2.92 times 10 to the -5 meters. So hope you enjoyed the problem. Uh, Once again, just a quick recap. We have a force being applied on the marble column. It's pushing it and causing it to shrink by delta L. We also have to find the stress and the strain. The stress is defined as, it's kind of like pressure. So it's this force that's being applied on a specific area. And so we just take the weight itself, which is 245 1,000 times 250 divided by the area, which is 1.4 meters squared. We get the strain 1.7 times 10 to the fifth power. And then we go ahead and use Young's modulus to compute the stress. Young's modulus relates the stress to the strain. We rearrange the problem by multiplying, both sides by the strain and dividing both sides by Young's modulus. So, we end up, these two are going to cancel and these two will cancel. So you have a new equation for the strain, and it becomes 3.4 times 10 to the -6. Remember, it doesn't have any units because the units for stress and Young's modulus cancel out. And then in the last page, we again use a different definition, conceptual definition of strain, which is change in length of original length. We use that to compute the change in length. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.